slightly above the bound axis or below bound axis. Okay, so they are not as strong compared to the sigma bound. They do not occur by themselves, and they're always associated with the sigma bound. There has to be a sigma bound connecting the two atoms together before the pi overlap can start. Okay, so those are the two different types of overlapping that happens in pretty much all chemical bonds there. And the chemical bonds that we know of now, we have single bound, we have double bound, triple bound, quadruple bound, so on and so forth. As long as you count the total number of electrons on the central atom there, as long as you have 8, or an exception to 8, you can have 10, 12, whatever number of electrons, as long as you have enough space there. So double bound requires 2 sets of overlapping orbitals there, and the two pairs of electrons. And triple bound requires 3 sets of orbitals and 3 pairs of electrons. And there's always a sigma bound in there. So sigma bound and multiple bound is a relationship there. Single bound, sigma bound, these are the two terms that we use interchangeably. Sigma bound means a single bound. Single bound means single bound means a sigma bound there. Okay. Now a double bound would be 1 sigma, 1 pi, and triple bound will be 1 sigma, 2 pi. Now the importance here is that most of the atoms that are capable of forming multiple bounds are nitrogen, carbon, oxygen, phosphorus, sulfur. Happens to be those atoms that are important in biological processes there. In the biosystem there, in the living things there, the lipids and the proteins and fatty acids there, that's where the carbon and nitrogen and oxygen, phosphorus, and sulfur comes in. Okay, so these are the atoms that are capable of forming double bounds there, or triple bounds for that matter. And these are biologically important atoms in most of the biosystems there. Okay, so when you're dealing with organic molecules there, you're dealing on a regular basis with double bound and triple bound there. And you hear the term hydrogenated oil or unsaturated fat. Well, that has something to do with the double bound there. And saturation is something that we use to measure in terms of the total number of electrons there. If you have double bound between the two carbons there, we say that's an unsaturated carbon, because each carbon technically requires a set of 4 sets of electrons there, 8 electrons there. And if you have a double bound between them, well, that's an unsaturated situation. If you have a triple bound, that's also unsaturated. So let's take a look at the bounding theory that we have talked about so far. Using methane as our example, methane CH4. Okay, so when you look at CH4, the molecule of CH4 there, the geometry, molecular geometry, electron pair geometry, or electron group geometry, both are tetrahedral. Okay, when you measure the bound angle, it's 109.5. Okay, and when you measure the bound length, it's identical, 110 picometer in length. The bound energy, each carbon-hydrogen bound stores about 414 kilojoules per mole of energy. That means if you need to break the carbon-hydrogen bound, you have to supply 414 kilojoules per mole of energy in order to break the bound there. Now, the problem here is that if you look at the valence electron of carbon, this is the valence electron configuration for carbon. Carbon group 4A, total of 6 electrons. The 1s, the 2 electrons on the 1s orbital is the core electron. They do not participate in chemical reaction. So you got 2 electrons on the s orbital, 2 electrons on the p orbital. Now these 4 electrons are not identical based on the old theory. And these 2 electrons will have a slightly lower energy requirement as these 2 electrons. Yet, how can carbon, an atom with 2 different types of valence electrons, form 4 identical bonds with hydrogen atom? Well, based on the old theory, these 2 electrons will form 1 type of carbon-hydrogen bound. These 2 electrons will form another type of carbon-hydrogen bound. So we should expect to have 2 different types of carbon-hydrogen bound, but the experimental measurement there, all bounds are identical, 110 picometer in length. So how do we explain, how do we reconcile this particular contradiction here? Well, Linus Pauling, the chemist who developed the electronegativity table, among others, and he suggests that the old valence bond theory has to be modified in order to explain what we observed in the laboratory. That is, we can, well, if you look at the number of orbitals here, there's one orbital, 2s, and there's one orbital in there, 2p, px, py, pz, total of 3 orbitals. Now we have 4 electrons there. We got 4 rooms. Why do we crop them into, well, in this case, if you draw it out, you will see 2s, 2 electrons in here, 2p, that's px, py, pz. And according to the old electron theory that we had there, electron distribution, we would have 2 electrons in here. And this room vacant. As a hotel manager, you say, well, you got 4 guests, you have 4 rooms. Why don't you just treat them nice? Give each person a private room instead of having these 2 occupy the same room while this room is not even being used. Well, so Linus Pauling suggests that we mix the available orbitals together and we form a new set of orbitals. We call them hybrid orbitals. Okay. And then we put 1 electron in each of the hybrid orbitals there. Now the hybrid orbitals are actually with the same energy. So assuming you have these two sets of rooms there, 4 rooms on different level in a hotel. Well, let's just tear it down and then build a new hotel with 4 rooms there. Okay. And they're all on the same level, they all have the same energy there. Okay. In this case, if we have a new set of orbital with the same energy, we can put 1 electron in each of those 4 rooms there. And then when the hydrogen comes in to form the carbon-hydrogen bond, each hydrogen will bond with an electron with the same energy of the other with others. So you end up with the identical bond of carbon-hydrogen, 4 carbon-hydrogen bonds there. So with the S, px, py, and pz, we can form a set of 4 hybrid orbitals, and then each hybrid orbital is going to point towards a different direction there, ending up with the tetrahedral structure. So if you look at the old versus the new, the orbital hybridization theory, this is what happens in the old theory, where we have electrons distributed. This is after the hybridization. You have a new set of hybrid orbitals there, where each orbital has 1 electron in them. And then each orbital has 1 electron in them. Well, when the hydrogen atom comes in, each hydrogen will bond with an identical orbital, with an electron in with an electron in the hybrid orbital there with the identical energy there, and they form identical bonds there. Okay, so when the hydrogen comes in, each one will actually bound, and you form an identical carbon-hydrogen bound in that situation. So this is what the hybrid orbital hybridization is all about. And we're looking at how many rooms do we have, how many valence electrons do we have. And we reorganize the rooms that we have and generating a new set of orbitals with the same energy and putting all the electrons in there. And then when other atom comes in to form the chemical bond with the same atom, you would end up with